Hey everybody, Swarsky here. We are officially in Unit 8, so if you want to take a second, pause the video, make sure you get that Unit 8 packet that you should have grabbed. If for whatever reason you don't, just make sure you have a separate sheet because you're going to want to do some practice. Not a big deal yet. We're just kind of doing some property stuff, but you are going to want to make sure you pick that up. You have today, tomorrow. We are going to be kind of in something that you'll want to have the packet by Monday. Okay, so again, let me know if you need to print it out or if you need me to mail it to you. Remember also I sent an email, you can print it out. Or the big one is come pick it up. It is waiting for you at the front office. But we are going to start out, we are working our way into the big and the bold trig ratios and law signs, law cosines. But first we need some properties and some understandings of what we call radicals. And we're going to be able to get some properties there. And like it shows in success, we're going to be able to do what's called rationalizing denominators. It's kind of the biggest combo of stuff. Let's get started. So the first big question is, what is a radical? A radical is anything with a square root. So this is a radical. Okay, well, even this is a radical. It can just be solved or simplified. This is a radical. This is a radical. Anything with the square root, right? 2 times, that's a radical. So they can look all different kinds of ways, but the big thing is that a radical has a square root in it. And even besides that, a square root itself is simply another way to write, instead of having something exponentially as like a square, a square root is half powers, okay? So it gives us a chance, we look at it as half powers or fractional exponents. And that's, we just use a different symbol, and that's what our radicals are, our square roots. So how are we going to combine them? The big one that we're going to be using, you can add them, subtract them, there's different properties for that, but the big one that we're going to kind of hone in on is these multiplying and how we can multiply them. And it looks like that, okay? We kind of treat these like terms. So you're always combining the radicals that are together. So if there's any common radicals, you'll always just multiply those together. And if you have any coefficients or just values like that, you'll just multiply those separately for that. And I'll kind of give you a better idea what that means. So the first one here, if I have root 2 times root 2, 2 times 2, that'll give me, I'll still keep the root 4. And then root 4, I can always think, can I simplify it? And yes, I can. So I can get to a value of 2. But the big one is that I'm always multiplying whatever's in the radical, okay, whatever's inside the square root, and it stays inside the square root. So root 2 times root 2 is root 4. And then I look at it, and I always say to myself, can I simplify? Can I simplify? Can I simplify? Okay? The next one here, why don't you try and see again, the only hint I'll give you is that radicals multiply with radicals. And the numbers themselves stay separate. So see if you can figure that out before I do here. Okay, so I'm multiplying the root 5 and the root 5. This 2 stays, and root 5 times root 5 is root 25, which actually can be simplified. These are kind of nice. They're perfect squares, we call them. So root 25, hopefully you can see that that's 5. So I'm really doing 2 times 5, which will give me 10. Okay, so again, we kind of think about it as like terms. Kind of the phrase, it's a little different than with variables, right? But these would be the same kind of thing. Okay, radicals, you multiply the roots together, you multiply the coefficients together. Okay, try this one out. Okay. So some of you might have the ideas that, well, if I ever square a square root, I simply just get the number inside. But why is that? This square means I'm multiplying whatever's inside there. So root 11 times root 11. Well, that's the same thing like we did up here. 11 times 11 is 121. That's still a root. The square root of 121 is 11, which is why, or actually another way to think of that is if I put this as the fractional exponent, if you remember your properties of exponents, if I'm multiplying powers, I'll just add those up. So this is really like saying 1/2 and 1/2. It's 11 to the first power, or just 11. So multiple ways to see it, but the big one is if I ever square root, I always just get the value inside that radical. Okay, another step up. Let's see if you can do it. Give me this one here. Okay, a couple ways to think about it. I can either think about it distributing this exponent to the 2 and the root 5, so then I'd get 2 squared times root 5 squared, which means it'd be 4 times, and then just like we had here, root 5 squared would just be the value inside, so I'd get 20. Or I can look at it a little different, and I can actually do what this says, 2 root 5 times 2 root 5. So now I'm kind of in this setup where I'm doing the like terms. 2 times 2, root 5 and root 5. And then I can simplify that way. 4 times 5, which will still give me 20. Okay? All right. Why don't you go through these in the next 4? I'll give you a second. Pause that video. See how far you can go. See if you can get all 4 of these. I know I'm giving you a little extra challenge here, but let's see how you handle it, and then we'll talk about it. Okay? All right. So in this case, we have root 3 and root 5. Well, if I multiply those together, I get root 15. Well, there's nothing I can do with that. It's not a perfect square. I can't do anything else with it. It just stays. It's our right to have that exponent or the radical value as a radical and just staying like that. It doesn't have to be a whole number. That's just what we would call a simplified version and combining. Might be asking yourself, well, why don't I just multiply it and do the decimal? Well, because it's rounded and it's not accurate. Same reason why we're leaving these in radical form. If I didn't, here's what I would get. You can see how much of a pain in the butt this is, 7/3. So if I do root 3, that's 1.73205, and on and on and on. And I'm multiplying that by what? Oops. I'm multiplying that by root 5, which is like 2.2360, Well, that's a pain in the butt to do. Doesn't it look nicer to do root 3 and root 5? And then even with that, if I had root 15 as a decimal is like 3.8729. See how much cleaner this is? So when I start combining these radical values, leave them as radicals. It's nicer numbers to deal with. They're easier to combine, manipulate, move around, and kind of deal with, and instead of looking at the decimal rounded form. The root 15 is the exact thing. That 3.8729 is all in that root 15. It's a cleaner look. Okay. Next one here, multiplying what I kind of reference as the like terms, the radicals. This 6 stays with it. 7 and 2 give me root 14, and it'll just stay that way. There's nothing more that I can do. Okay, I can't do 6 times root 14 and get something nice, so we just leave it like that. Okay, next one, now I have 2 sets of them. I have the values here, so that'll be 8. 3 and 5 will be root 15, and again, I leave it as such. How do I deal with the fraction? Well, if you look, like if I just got rid of this, and I just had 3 over 12, well, how would I deal with that? Well, I could simplify. I'd get 1 over 4. Perfect. I don't just have that. I also have that, or I also have the root, which means that stays there. Root 2 over 4. So again, just like I did with when I'm multiplying, I divide those like terms, or those coefficients, those number values in there. Okay? I'm not going to, well, I am. So you should be able to, oops, hold on a sec. Ouch. Hold on. Oh, my pen stopped. You should be able to look at these and be like, yep, I can do roots, 9, 16, 25, 36. Should know everything and be pretty comfortable out to 12. That's why I have those. So you should, whenever I see root 64, 49, root 25, all those what we call perfect squares. Okay. 121, 144, all that. And I mean, even you could even go farther out to 13, 14, 15 if you want to. But if I can do that, recognizing these perfect squares is going to be very beneficial to us in this next piece, okay? Which is simplest radical form. Because if I look at this root 27, I can actually make that a more condensed radical or a simplified radical, okay? And I treat that like lowest common denominator kind of stuff, where I say, all right, well, 27, I can break that down into some different values. And the big one is root 27 is the same as if I were to have 9 times 3, right? And the reason is because just like with, if I had that split, I could get root 27, right? Well, there's one of these that's more important than the other one, and that would be this guy. Can you see why? Because this perfect square. And that's what I want, because then this can actually give me a value, right? So this root 9 times root 3, I can simplify that. Root 9 is 3, and then I still have this root 3. This is simplified radical form. And what also is, that is the same as that. Well, why would I want to go from root 27 to root 3 over 3? Well, the short answer is when you're dealing with smaller values. The other one is a lot of times it's easier to combine. You're not dealing with you're not multiplying by 27. Instead, you're dealing with the 3s. It's just an easier situation to deal with, and we should be able to get it in simplified radical from there. So the big piece when you're simplifying radicals is you're splitting it, and you're trying to pull out the perfect square. 25, 16, 9, 49, this stuff. You're looking for these values here that you can pull out of that number. So you need to know your multiples when you have that. And you're trying to get to the simplified radical form. Okay? So here's what that looks like. I look at this with 200. Now there's different things that I can do, but what I'm looking for is the largest perfect square that I can pull out. Okay, because I can do, like in this case, I could split this 4, and then that would be what, 50? Which is fine, but then I can simplify this farther for what I'm going to do. And I'll actually do that here in a second. So if I want the simplified radical, I want the biggest perfect square that I can pull out. Well, in that case, that's like that. Well, why did I pull out root 100? Well, because root 100 is 10, and I keep that root down. Okay, so I'm just simplifying this into something easier to deal with. Okay, now, something to think about. What if so some people ask, well, what if I don't do that initially? What if I use and I say, all right, well, I can divide this by 4, or 4, not 40, 4. Okay. And remember, why am I putting those square roots in there? Because I'm just splitting the square root into two things, right? If I saw root 4 and root 50, I could change that into root 200. So I can go the other way too, where I can split these into different roots. Okay. Well, I have a perfect square here. Good. So that's 2 root 50. But you have to ask yourself, can I keep simplifying this root? And the answer is yes. And remember, we ended up getting to 10 root 2. And we're going to see if we can keep doing that. Okay. Well, 2 root 50, well, I can split this into it. There's another perfect square built into this one, and that would be 25. I'm going to move that up here, right? So if I have 2 root 50, root 50, that can be split to root 20, or 2 and then root 25. Well, this is the one that can get split. So now I'm sitting at 2, and this is all being multiplied, root 2. Combine, I end up in the same place. And now that's simplified, I can't go any further. So you see, I'm taking more steps, so why not look for the largest perfect square right away and see if you can go from there. Okay? Let's try the next one. Give it a shot, see if you can't pull the biggest square, perfect square out, simplify it down, see how you can do. Okay? Biggest perfect square I can get is 9. Root 9, root 5. So then this ends up being root 9 is 3, and I keep that root 5 there. Give it another shot. Try these next two. hit pause, try it out. We get, right, perfect square, root 4 is 2, and I still have this root 11. Same thing with this one. Biggest root I can pull out, perfect square, I can do is 16. Okay, you might have done root 4, but then you'd have to see that you could still do more. Okay, root 10, root 16 is 4, root 10. Woo! Simplified radical. All right. Last piece is what we call rationalize the denominator. That means when we rationalize, that means we have a radical in the denominator spot. Why is that icky? When we start trying to combine or multiply or do stuff, it just causes too many problems. Trying to keep everything organized and in there. So what we want to do is we want to rationalize. Or another way to say that is get this out of the bottom. Okay? So then I do not want radicals or roots in the denominator spot. Just in the long run, it causes too many problems when we start trying to combine, and just too many math errors start occurring. So the easier thing to do is, before we even start that, if I see a radical in the bottom, get it out. And that's what's called rationalizing the denominator. Okay? We turn it into a rational number as opposed to an irrational number, right? Irrational goes on forever. Rational numbers are repeating or terminate decimals. Okay? And here's how I do that, or here's how to think about it. Now, what I want you to realize is that as long as I multiply the same thing top and bottom, so let me just look at, let me look at this where I have 3 root 2. If I multiply by a fraction, right, 1 times 1, well, I didn't change the fraction, right? Well, what if I do like 7 times 7? Well, I'm still only multiplying by 1. Do you see that? Well, what if I do root 7 times root 7? Well, I'm still just multiplying by 1, okay? Well, if I want to rationalize this or get this out, there's a specific root that I can multiply by that'll turn this into a rational number, and specifically into a whole number. Can you see what that is? It is root 2. And as long as I do it to both pieces, this is still just multiplying this by 1. Okay, just a very specific looking 1. Okay? So now when I multiply, remember when I multiply fractions, I go straight across. Root 2 times root 2 is 2. And then I just keep 3 times root 2. That doesn't change. This is now the rational, or the rationalized version of this. And again, the reason why I want to do that is that as we go through, having a radical in the denominator spot just causes more problems than we want to deal with. So, if you would, hold on 1 second, everybody. Swirsky. Large. Yes. Yeah, bye. Sorry about that. Okay, why don't you try seeing if you can do this one, or try and think of at least what would I rationalize. To rationalize this, what would I need to multiply this piece by? Say it in your head, say it out loud, scream it from the rooftops. The answer to that is 3, and the reason why I'm doing that is because root 3 times root 3 gives me a rationalized denominator of 3. So now I say, all right, well, what about the top? Well, remember, I'm just doing a funky looking version of 1. So now I have 12 root 3. Ask the question, am I done? Is this simplified? Or is there something that I can do to make it more simplified? And the answer to that is, yes, I can do that more simplified right here, right? 12 divided by 3 is 4. So really, this can even be nicer, because if I can get it out of this fraction here, it looks even cleaner. So this and this are the same thing. Oops, one too far. Why don't you try these last two? See if you can rationalize the denominator, get it down to simplified, get it down to the most simplified form. Let's see if we can do that. Okay. Remember, all I'm doing is multiplying by a fancy version of 1. In this case, it's to make sure I can get this to a different, to a a whole rational value. Okay? Well, what do I need to multiply it by? Well, the same value. And the reason is because then this turns into 7. And then I just keep the same thing on top. And if I can simplify, which I can't, that's simplify. That's rationalize the denominator. That's the simplified radical form. Next one. Ooh, I'm giving you a little bit of a challenge. We're multiplying both of these top and bottom by root 3, right? Root 3 times root 3 is 3. And then if I just want to look at the whole thing, 3 root 2 times root 3, well, that means I can combine the radicals, right? So 3 root 6 and 3 divided by 3 is 1. So those go to 1, and all I'm left with is root 6, my friends. All right. Ta-da! Simplified radicals and radical properties in general. Very nice. I know it was a little bit of work, but hey, we did it. What I want you to do, there is practice to be done. Skills Core Extended from page 3 to page 5. Core is the required. Let me know if you have questions. I have solutions in the daily doc. I hope you have a great day, everybody. Take it easy, stay safe, and I will see you on the next one.